Hello, welcome to the channel. My name is Qiujiang Lu, the author of this paper, Deriving the Imaginary Unit and the Euler's Formula from First Principles, and Discovering the Existence of Rotation Factor Set. The mysterious imaginary unit has eventually been proven real. Here in this video, we are going to explore the fundamentals of the imaginary unit and the complex numbers. In the process, we may gain more appreciation about the wonder and elegance of math and nature. More than 400 years ago, the imaginary unit I was discovered from solving the cubic equation. Here, from first principles, we are going to prove the imaginary unit is real. From the cause and the effect viewpoint, it's natural to ask the basic question: is the imaginary unit the cause or the effect? If the imaginary unit is the effect, it's generally unfeasible to find the cause by studying the effect within the effect's scope. From this point on, until specifically mentioned, we assume there is no existence of the complex number system, so that our mind is not influenced by the existing concepts, and will focus on creating a number system from first principles. Creating a new number system. Where to start? First, let's check the position stretching by real numbers. In the case of one-dimensional line, here RE denotes a real number axis. O is the origin. A point in the axis may be represented by a position number. For example, the point here is represented by position number 2. Multiplying 2 by 3 makes the point stretch to the position represented by number 6. It's noted that, like a vector, a position number also implies a direction, which is from the origin to the point. As we can see, the multiplication by a real number causes the position stretching only, without direction change. In the case of two-dimensional plane, here RE denotes a real number axis, and the OR denotes the axis that's orthogonal to RE axis. A point in the plane may be represented by a position vector. In this illustration, this point is represented by position vector p. Multiplying the vector p by 2 makes the point stretch to the position represented by position vector 2p. Again, as we can see, for the vector, the multiplication by a real number also causes the position stretching only, without direction change. Here, we may notice that the position stretching represents a linear motion, but in real life, besides the linear motion, there is another basic motion type. Two basic motion types. In the physical world, there are two basic types of motion: linear or translational motion, and rotational motion. The linear motion, like the car here, it moves along a straight line without direction change. The motion may be described by position stretching and the multiplication by real numbers. The rotational motion, like the car here at the intersection, it makes a turn or rotation. Nature tends to be perfect. Then one may think rotation is also a basic motion type. There likely exists a new type of numbers that describe the rotation by multiplication as well. By analogy with real numbers, rotation factors are introduced to make the position vector rotate by multiplication. Rotation factors may also be called rotation numbers. Here, we mainly use the term rotation factors to be more in line with physics and the cause and the effect. Here is the rotation factor definition by statements. A rotation factor Q of angle delta is defined as a factor for multiplying to a position vector and making the vector rotate counterclockwise by angle delta relative to the origin point of the vector with the vector's magnitude unchanged. This figure illustrates the definition. A rotation factor Q is rotation angle specific. In the figure, delta is the rotation angle for rotation factor Q. O is the origin. Point P is represented by position vector bold P. Point P sub delta is represented by position vector bold P sub delta. The angle difference between the two vectors is delta. Here, multiplying rotation factor of angle delta to vector bold P makes it rotate to the position represented by vector bold P sub delta. It should be noted that the rotation factor changes the direction of the vector only without stretching or changing the vector's magnitude. Also, the rotation factor itself does not rotate. It needs a target that implies a direction, such as a vector. At this point, the existence of rotation factors is still an assumption. If the consequences of the assumption are consistent with existing results, it's then considered true. Rotation factors have many attributes. Next, let's see some basic ones that are readily obtained. Rotation factor is angle dependent. Rotation factors are a new type of numbers as they can change vectors' directions and the real numbers cannot. In general, rotation factors are not real numbers, but the two angles 0 and pi are the exceptions. The rotation factor of angle 0 is the real number 1, as it produces no rotation for its target vector. And the rotation factor of angle pi is the real number -1, as it rotates the target vector by 180 degrees and reverses the target's direction. It's natural to think that the exact middle angle half pi between 0 and pi is also special. The rotation factor of the angle half pi is here defined as orthogonal rotation factor, in that it produces a 90-degree rotation for the target vector. Notation-wise, the orthogonal rotation factor is denoted as Q half pi, which is further succinctly denoted by a simple I. We are going to see the orthogonal rotation factor is very important. Next, let's check some rotations caused by the orthogonal rotation factor. In this figure, O is the origin. Point P is represented by vector bold P. Multiplying orthogonal rotation factor I to vector bold P makes it rotate to this position, represented by vector bold Pi. Multiplying I again makes vector bold Pi rotate to vector bold Pii. We then have the following results. Vector bold Pii is the vector here, which has a reverse direction of vector bold P. Thus, I squared equals -1. Similarly, here vector bold Pii has a reversed direction of vector bold Pi. Thus, I cubed equals -I. And further similarly, we have this result: I to the power of 4 equals 1. The concepts of motion and rotation factors have led to the discovery of a fundamental equation of position vector rotation. Next, we will derive the equation. In this figure, O is the origin. Point P is represented by vector ball P, which has a magnitude of r. Point P sub delta theta is represented by vector ball P sub delta theta. The angle difference between the two vectors is delta theta. Delta ball P is the difference between vector ball P sub delta theta and vector ball P. N hat is a unit vector that's perpendicular to vector ball P. Here, vector delta ball P equals the magnitude of the vector times u hat, which is the unit vector of delta ball P. Delta S is the length of the arc corresponding to the angle change delta theta, and delta L is the length of the chord of the arc. Delta L is also the length or magnitude of the vector change delta ball P. Taking the ratio of these two equations results in this equation. We just obtained this equation. As delta theta is approaching 0, this term is approaching 1, and the unit vector u hat of delta ball P is approaching unit vector n hat. Taking the limit of this equation for the derivative with respect to theta, this term becomes this, and this term becomes 1. U hat becomes n hat. So the result is this equation. We just obtained this equation by the definition of orthogonal rotation factor I. Multiplying I to vector ball P makes it rotate by angle half pi with the vector's magnitude unchanged. Here is the vector ball P. Multiplying I makes the vector rotate by 90 degrees to this direction, which is the same as the direction of n hat. The magnitude is r. Thus, we have this equation. From these two equations, we obtain this equation, which is the fundamental equation of position vector rotation. So, we have obtained this fundamental equation. It's important to note that the orthogonal rotation factor I appears in this equation. We will discuss the deep meaning and the implication of the equation later. Next, we introduced a new number system to represent the position of a point in a plane. Here, in a plane, point P is represented by position vector ball P. If we want to use a new type of number to represent the point, it's natural to use the term position number. So position number, lowercase p, is used to represent the same point. In comparison, position vector ball P has an explicit direction with an arrow pointing to the direction of the vector. Position number, lowercase p, represents the same point, P, and also has the same direction. That is, from the origin point O to the point P. For the position number, the direction is implied without the explicit direction arrow. Both have the same direction and the magnitude r. Thus, the same rotation factor concept can also be used for position numbers. The next topic is rotation factors are applicable to position numbers. Here is the definition of rotation factor for rotating a position number. Multiplying a rotation factor Q of angle delta to position number P makes the position number rotate to position number P sub delta with the implied direction changed counterclockwise by angle delta and the position number's magnitude unchanged. Next, about the fundamental equation of position number rotation. For representing the same point, rotation number has the same direction and magnitude as those of the position vector. Thus, the methodology for deriving the fundamental equation is identical to that of the position vector. In this figure, the notations remain the same except that the position vector bold capital P is replaced with position number lowercase p. This is the fundamental equation of position number rotation. It looks identical to the equation for position vector due to the fact that both position number and the position vector have the same direction and magnitude. Next, we will solve the equation to obtain the rotation factor dependence on rotation angle theta. To solve the fundamental equation, the relationship between position number and the rotation factor needs to be obtained first. In this figure, RE is a real number axis. OR is the axis that's orthogonal to the RE axis. O is the origin. P sub R is a point in the real number axis and is represented by real number R. The direction of the real number R is the direction from the origin O to the point represented by R. By rotation factor definition, multiplying rotation factor of angle theta to real number R makes the number rotate counterclockwise by angle theta and reaches the point capital P, whose position number is RQ theta. The point capital P is also represented by position number lowercase p. Therefore, by the definition, we have this relationship P equals RQ theta. Next, we will obtain the rotation factor dependence on rotation angle. This is the fundamental equation. This is the position number relationship with rotation factor. Inserting the relationship into the fundamental equation, we have this partial differential equation. For the derivative with respect to angle theta, R is considered constant, and Q is dependent on theta only. Then this equation is simplified as this equation. In this equation, the orthogonal rotation factor I is constant. Thus, we have this equation. For this obtained equation, denote phi equals I theta. We have this equation. The equation says that the derivative of Q with respect to phi equals Q itself. Thus, Q is the exponential function. Then we have this solution. Phi is given by this. Therefore, we obtain this final rotation factor dependence on rotation angle. The rotation factor dependence on rotation angle may be called rotation factor formula. The formula shows the existence of rotation factors for all angles. This result has profound implications. Based on the concept of motion and rotation factors, we have obtained the fundamental equation and discovered the existence of rotation factor set. The rotation factor set E is formed by all rotation factors. Here, rotation angle theta is real number, and the value range of the angle theta is greater than or equal to 0 and less than or equal to 2 pi. Next, about position numbers. Previously, from this figure, by rotation factor definition, position number P equals RQ theta. Thus, we have this position number formula, P equals RE to the power I theta. This formula means that multiplying a rotation factor of angle theta to a real number r in a real number axis makes the number rotate to the point represented by position number P. From this, we can see that position numbers are formed by real numbers and rotation factors. The set of real numbers is denoted R. The set of rotation factors is E. The set of all position numbers is denoted P. The set P represents all points in a plane. Each member in P may be constructed by a member in R and a member in E. This figure illustrates their relationship. From the perspective of describing motion of points in a plane, numbers may be classified into two types, real numbers and rotation factors. Position stretching is realized by a member in the real number set R. Multiplying a real number to a position number or position vector stretches the target's magnitude without changing the target's direction or orientation. On the other hand, multiplying a rotation factor to a position number or position vector rotates the target without changing the target's magnitude. Nature turns out to be magically perfect. The existence of real number set R and the rotation factor set E complement each other and complete the representation of the two basic motion types. Next, about 2D arithmetic. Discovering the existence of the rotation factor set and understanding its properties and the implications give rise to two-dimensional or 2D arithmetic. One of the main benefits of 2D arithmetic is to allow elementary students to use the familiar position and the rotation concepts of the physical world and solve practical problems from a higher dimension perspective than 1D without the deeper knowledge behind the rotation factors. Here, we illustrate how 2D arithmetic may be readily constructed. A rotation factor of angle theta may be denoted as this to hide the complexity to a beginner. The square brackets appear to be a good selection in terms of being common and direct for typing from a standard computer keyboard. Rotation factors may also be called rotation numbers in direct comparison with real numbers. Let's see an example of 2D arithmetic. In the figure, the degree unit is used for angles. Multiplying rotation number 30 to the number 3 makes the point rotate by 30 degrees relative to the number's direction and reach 3 rotation number 30. Multiplying the position number 3, rotation number 30 by 2 makes the point stretch to 3, rotation number 30, 2, and multiplying rotation number 15 to 3, rotation number 30, 2, makes the point rotate to 3, rotation number 30, 2, rotation number 15, which is equal to 6, rotation number 45. A mobile phone app calculator may be developed and used to calculate the rotation numbers. Next, the causality origin of the orthogonal rotation factor I is discussed. This is the orthogonal rotation factor I definition. Up to now, the I is still a symbol as Q half pi. One may still ask, what's Q half pi? To answer this question, it's noticed that Q half pi is a constant that's denoted by I, and it's also noticed that the pi is also a mathematical constant. From the causality viewpoint, investigating the cause of the pi may provide a hint for the cause of the I. Since the ratio of a circle's circumference c to its diameter d is a constant, this leads to the definition of pi. Pi is defined as the ratio of circumference c to diameter d. Both c and d are variables, but their ratio pi is a constant. By the same token, from the fundamental equation of position vector rotation, the constant I may be defined as the ratio of the term position vector partial derivative to the term position vector. The term partial derivative of position vector p with respect to rotation angle and the term position vector p are equivalent to variables, but their ratio is a constant. It's the existence of the ratio being constant that causes the existence of the I as well as the existence of the rotation factor set. It's important to point out that the term partial derivative of the vector p and the term vector p have their respective directions, which are perpendicular to each other. As a result, their ratio I is a special non-real number constant and represents an orthogonal rotation. Next, we will construct a Cartesian coordinate system based on rotation factor set and obtain Euler's formula. In this figure, RE denotes a real number axis, OR denotes the axis orthogonal to RE. Point O is the origin. The point represented by a real number R in the RE axis has the direction of the positive RE axis. Multiplying a rotation factor of angle theta to number R makes the point rotate by angle theta to the point represented by position number p or Re to the power I theta. Then we have this equation. The point represented by number A in the Re axis and the point represented by P form a line that's parallel to the OR axis. The distance between the origin and the point represented by number B is the same as the distance between the point represented by P and the point represented by A. Applying the orthogonal rotation factor I to number B makes the point rotate to the point BI in the OR axis. Again, by the rotation factor concept, BI has a direction that's perpendicular to the RE axis and points upward. In the Cartesian coordinate system, the position number p is expressed by this equation p equals a plus bi. In this figure, from the definition of sine and cosine, r cosine is a. We have this equation. R sine is b. We have this equation. Inserting a and b back to this equation and combining with this equation, we then obtain Euler's formula here. The deep meaning behind Euler's formula turns out to be the concept of rotation factors and the existence of the rotation factor set. The position number p in this equation is equivalent to the definition of the complex number. The orthogonal rotation factor I here is equivalent to the imaginary unit. The discovery of the rotation factor set along with the orthogonal rotation factor I finally reveals the causality origin of the mysterious imaginary unit. In the end, let's summarize the key points. Fundamental equation of position vector rotation has been discovered. Causality origin of imaginary unit has finally been found. The existence of rotation factor set has been discovered. From the point motion perspective, numbers may be classified into two basic types: real numbers in set R for position stretching, rotation factors in set E for position rotation. The existence of rotation factor set E is a gift from nature. It's believed that if advanced aliens exist, they may also have the similar concept about the existence and the characteristics of the rotation factors, although their mathematics may take radically different forms than ours. Thanks for watching.